Hi, this is John Whitaker for the Mathematical Analysis 2 class, and this is our 30th video lecture. And we had just ended the last video lecture talking about pointwise bounded, uniformly bounded for sequence of functions. I'm going to give an example of something that is uniformly bounded to start the day off. It's a very simple example. And if we set up a sequence f sub n, such that f sub n of x is equal to sine of the quantity n times x, then f sub n as a sequence is uniformly bounded on R, and then I'll just say by the number 1, so that's the one number that bounds all of the x values for all the n's. That was an example. What I'd like to write out next is what we're interested in terms of questions. And these are related, these questions are related to the fact that we have, in analysis 1, noticed that if you give me some kind of bounded sequence, numbers, then they had to have a convergent subsequence. Here's what we're interested in. We want to know a question of interest. Is if the sequence of f sub n is bounded in some sense will the sequence have a subsequence that converges in some form, pointwise, uniform. Okay. And the answer in general is no. So what else do we need to require to make this happen? And another question is whether or not every pointwise convergent sequence of functions f sub n contains a uniformly convergent subsequence. Again, in general, the answer is no. So we might need some more conditions. What conditions do we need? Well, before we look at maybe some facts and build up to some conditions that might answer those questions or help ensure that those questions are answered in the affirmative, what conditions will answer those questions in the affirmative. Let's look at this example. This is out of our case. F sub n of x be defined by x squared over x squared plus the quantity 1 minus n times x to b squared, where we're going to have this function defined for x's on 0 to 1, and n runs from 1 forever. Note, complex norm here is going to be less than or equal to 1. And so that means that the sequence of f sub n's is uniformly bounded on 0 to 1. So bound by 1 is easy to see. You see, we're having x squared divided by a squared plus some non-negative amount. So that's going to be less than or equal to 1. This is a closed interval here. Also, the limit as n goes to infinity of f sub n of x. Okay. So for each particular x, if you fix an x, you let n get really, really big. This number is going to become a really big negative number squared, becomes really, really big positive. Whatever x is, when you start dividing it by a really, really big positive number, that's going to go to 0. And this happens pointwise. Okay. Now, another thing to observe is that f sub n of the number 1 over n, which is for each n going to be n between 0 and 1, the n of the closed interval, but that's going to be equal to x squared over x squared plus 1 minus, well, the n times, I'm letting x be 1 over n, to b squared. Now, of course, that's 1. 1 minus 1 is 0. 0 squared is 0. We just get x squared over x squared, so that's 1. And that's enough for us to be able to determine that this sequence is not uniformly convergent. That no subsequence of it can be either. Let me write that down. Thus, no subsequence of f sub n can be uniformly convergent. And that definition can be seen from the Cauchy criterion for uniform convergence as well. Okay, so that's what we got. Write down what E was in this case. That's what I said. All right, here's a definition that gives a requirement that can help us about the two questions. It says a family, script F, that's a script F, of complex functions. That's a collection when we say family. F defined on the setting. It's said to be, well, E is in a metric space. It's said to be XY continuous, if for each epsilon greater than 0, there exists a delta greater than 0, such that f of x minus f of y will be less than epsilon whenever the distance between x and y is less than delta, and that's for all f, the functions in our family of functions, script f. I'll leave it there. Of course, we're saying that x and y has to be for me whenever the distance between x and y is less than delta. As a comment, let me just say, what we're saying here is that the same delta works for all the f's in this family. Okay? So that's kind of the difference between equicontinuous and just each one of the functions, the collection of functions being equicontinuous, and each one of the functions being uniformly continuous. Okay, as a fact, and I'll just state this. It says, if script f is an equicontinuous family of functions, okay, on E, and we have F's an element of this family, then F is uniformly continuous. On E. Let's look at an example. So as an example, we consider F to be the collection of functions that look like f sub n of x equal to x sub n. And we're going to define on 0 to 1. Then F is not an equicontinuous collection. And it turns out that for x bigger than 1, these functions aren't uniformly continuous. Another example, this is a very simple example, but if you let script f be the collection of all f sub n of x, it's just equal to n, so just these constants. This is equicontinuous. On R. So those are two examples. Let us change this from 0 to open 1, okay? So I want to go back. I want to change this from 0 to open 1. So I made that change, okay? Let's do that. Next, we're going to be looking at a theorem. If f sub n is a pointwise bounded sequence of complex functions on a countable set E, then f sub n has a subsequence f sub n sub k such that f sub n sub k of x converges for every, so this is pointwise, for every x in E. The proof's a very interesting one. First of all, we let x sub I be the points of E, so we said count collection, arranged in a sequence. Since f sub n is pointwise bounded, that's what we're assuming, then f sub n of x sub 1, the first point that we're labeling E, is bounded. There's a number that's bigger than, that's the value, or the norm of f sub n of x sub 1 for all n. Okay? And thus has a convergent subsequence f sub 1 of k where f sub 1 sub k of x sub 1, that's what we mean by this, converges. Okay. That's what we have. That's this figure dependent. All right. So what we're going to do is we're going to construct a sequence, or a sequence of sequences. Okay, so let us examine the sequences S of 1, S of 2, S of 3, and so forth, represented by okay, so here's S of 1. S of 1, so it's equal to F sub 1, 1, F sub 1, 2, F sub 1, 3, and so forth, forever. S sub 2 is equal to F sub 2, 1, F sub 2, 2, F sub 2, 3, let's add one more here, F sub 1, 4, and here let's have F sub 2, 4, and so forth. S sub 3, it's got F sub 3, 1, this is where I'm noting it, F sub 3, 2, F sub 3, 3, F sub 3, 4, and I'll do one more. S sub 4, that's 4, 1, 4, 2, 4, 3, 4, 4. Okay. And here's how we're making those sequences, each one of those S of 1s. This array of sequences here. It's going to have the following property. Okay. Which have the following property. First thing is that S of n is a subsequence of S of n minus 1, and that's true for n being equal to 2, 3, whatever. B, F sub nk of x sub n, okay, converges as k goes to infinity. And C, the order in which the functions appear is the same in each sequence. What we mean by that last one is that terms in this sequence and the lower sequence, they have to maintain the order, be a subsequence of the previous. All right, so we define S to be the diagonal sequence f sub n. So here's what S is. It's f sub 1, 1, f sub, the next term is f sub 1, 2, 2, f sub 3, 3, and so forth. Then, m sub n of x sub I converges as n goes to infinity. And that's true for all I. I'd like to go back to our array for a second, explain some of this. Here's our array. Here's what we're doing. Look, this sequence here converges for x sub 1. Okay? And that's one of the points in any. All the points in E can be labeled as x1, x2, x3. So that's how we get all the points in E. So this sequence converges if we just look at it for x sub 1. What we're going to do is take a look at this sequence acting on x sub 2 with a balance sequence. Okay? So that would be a balance sequence for x sub 2. And then from that, we pick a subsequence of that converges. Okay, so that's how we get this x sub 2. So this guy converges for x sub 2. And then from that, we look at that sequence applied to x sub 3, and it's a bounded sequence, so we get a subsequence of that converges for x sub 3. And that's what we're calling s sub 3. And so here, when you take x sub 1 and look at f sub n acting on it, okay? After some point, the nth, so f sub n acting on x sub 1. Well, all of these terms here are part of these first term. And so, since the first term converges, there's a spot from then on that's really close to whatever it converges to. Now, when you take f sub n of x sub 2, after some point, okay, all of the terms of the sequence here, all the terms of the sequence are a part of this previous one from here on. And at some point within this sequence, the f of x sub 2, f sub n, f of this sequence applied to x sub 2, I should say, is going to be really close to what it converges to. Okay? And so the same thing is going to happen here for this diagonal sequence, and so on. So each one of these things converges. And that's our proof. Okay. Next, we're going to write a theorem. It says if K is a compact metric space, if f sub n is an element of C of K. Remember what those are. Those are the collections of complex value functions that are continuous and bounded. Okay. And that's true for n equals 1, 2, forever. And, got one more condition, if f sub n's converges uniformly then the f sub n as n runs from 1 to infinity is xy continuous on k. Let's look at its proof. That epsilon will be greater than 0 be given. So we need a delta bigger than 0 such that for all x and y in k with the distance between x and y being less than delta, then the distance between the output values of f sub n on x and y will be less than epsilon, and that's true for all n, equal 1, 2, 3, 4, forever, okay? Okay. Now, since the f sub n converge uniformly, then we know it's true, okay. There exists an integer n so there exists this integer n such that for all n and m bigger than or equal to this big N, the norm of f sub n of x minus f sub m of x will be less than epsilon over 3, anything that any positive number that I want, I'm taking epsilon over 3. And that's true for all x in k. And that we're using the Cauchy criterion for uniform convergence. Okay. Thus, in particular, what we have is that the norm of f sub n of x minus f sub b n of x will be less than epsilon over 3, and that's for all x element of k, and for all n bigger than or equal to this big N that we have. Okay. Now, since as a fact, since continuous functions on a compact set are uniformly continuous, then there exists a delta sub n, and it's greater than 0, such that for all x and y element of k, with the distance between x and y being less than this delta sub n, Then f sub n of x minus f sub n of y will be less than epsilon over 3. Now, let delta be equal to the minimum between delta sub 1, delta sub 2, all the way up to delta sub n, big N.
Of course, we're picking the minimum here because what we want to have happens for
X's and Y's close together. So we want a bunch of things to happen. And so we want to make sure that the X's and Y's are close enough together to make all of those things happen. And so what we say then is for all X and Y in K with the distance between X and Y being less than this delta, then f sub n of X minus f sub n of Y inside the norm will be less than epsilon over 3. And that's true for all n, for n equaling 1, 2, 3, all the way up to big N. Okay, so that's the only n's I'm talking about this time. Now, if we look at n, little n's bigger than big N, okay, and we take a look at still x's and y's that are less than this particular delta that we have, then if we look at f sub n of x minus f sub n of y, this line up here, I'm getting what I want really for n's up to big N, okay? But I got to do more than that. I got to worry about all the n's. So what about the n's that are bigger than this big N? Well, this guy is going to be equal to, I'll rewrite it as f sub n of x minus f sub big N of x plus f sub big N of x minus f sub big N of y plus f sub big N of y minus f sub little n of y. And then I'm going to use the triangle equality and say this is less than or equal to f sub n of x minus f sub big N of x in norm plus the norm of f sub big N of x minus f sub big N of y plus the norm of f sub big N of y minus f sub big N, f sub small n of y. Now I want to have this be less than epsilon, okay? This guy right here is less than epsilon. I've already got less than epsilon over 3, so I makes it less than epsilon. That's what we need for that delta. We hope that this guy now begins to be, I can make that be less than epsilon. Okay, well, here, I need to be able to bound each one of these parts. This guy will be able to do what we said earlier, right? Epsilon over 3. Okay, the other guys, we're going to have to use something we've already used, and that was in the previous work. And that is our previous work had given each one of those parts in their norm, I should say, to be less than epsilon over 3. that's going to be less than epsilon over 3 plus epsilon over 3 plus epsilon over 3. Sorry, let me go back. This part's less than epsilon over 3. This part's less than epsilon over 3. Okay, because of the uniform convergence. Okay, convergence uniform for this guy. This guy has to do with just this one being uniformly continuous. Okay, that's the big end being uniformly continuous. And that's the reason we get the epsilon over 3 for both of them.
And so, what we have then
is that tells us that that the f sub n's is x y continuous on K, and that's what we're trying to prove. All right, so that is that theorem. The next theorem's lengthy. Let's go ahead and do it. It says if K is compact, let's do it this part. If f sub n is an element of C of K for n equals 1, 2, 3, forever, and if f sub n is pointwise bounded, and xy continuous, on K, then we got two conclusions. Part A is that f sub n is uniformly bounded on K, and part B is f sub n contains a uniformly convergent subsequence. For the proofs, well, I'm going to assume hypothesis, that is, we're going to let K be compact. F sub n be an element of C K for n equaling 1, 2, 3, forever. And F sub n being pointwise bounded. And it will continues on K. For the part A, we're going to show uniformly bounded for the sequence. Let's start off with letting epsilon be equal to 1. And so, since the sequence f sub n is xy continuous, there exists a delta bigger than 0, such that for all x and y in k, with the distance between x and y being less than this particular delta, then the output values for f sub n of x, f sub n of y, their distance from each other will be less than epsilon. And that's true for all n, 1, 2, 3, forever. And so the epsilon here was 1. Now consider the collection of neighborhoods n sub delta of x, where x is an element of k. So for each x, we looked at the delta neighborhood about it. That's the distance, or if you will, the collection of objects. Let me write it down. Where n sub delta of x is the collection of all y's, element of k, such that the distance between x and y is less than delta. So that's what we have. Then this collection is an open covering of k and since k is compact, has a finite subcovering. And so what we mean by that is that there exists a finite collection of points in K, say x sub 1, x sub 2, x sub 3, all the way up to x sub p, such that the collection of n, the neighborhoods, the delta neighborhoods about x sub I, where I runs from 1 to p, covers K. Now, since f of sub n is pointwise bounded, on K, that means for each x sub 1, x sub 2, all the way up to x sub p, there exists a number, a positive number, I'm going to call it m sub x sub I, that's greater than 0, such that this norm of f sub n of x sub I that will be less than m sub x sub I, and that's for all i's. For all i's, which i's? Let me write it here. I sandwiched in between 1 and p. Okay? And this is it's going to be true for all these i's and for all n's, for all natural numbers n. Okay, that's what we have. just to reiterate something. Excuse me.
I think I failed to pull this over, I'm sorry.
We'll go back over this. Look, we were talking about, sorry I missed that. We were talking about a compactness of K where we had no recovery, so we get a finite subcovering. That's what this does. Okay? We get this finite subcovering from these open neighborhoods. And then what we're doing here is that F sub n is a pointwise bound, on K. Okay, that means that for each x in K, there's some number out there that bounds F sub n of x for all those n's. So that bound depends on x. But here, we'll just look at those finite points, those x sub 1 through x sub p, and talk about having finite number of bounds that we need for these x sub 1s, or x sub 2 all the way to x sub p. Okay, that's what we have. I'm sorry. Turn it. Okay. Well, through the finiteness, we'll get to pick the maximum, so we'll let m be equal to the max of all of these guys. Then we know that F sub n of x sub I will be less than m, and that's for all n and I equaling 1 all the way up to p. Now, let us just let y be an element of K. We're trying to find some number that will bound the output values of all the y's. Okay, so I'm just picking one of them. And hopefully I have this one particular bound that doesn't depend on the y. And so it's supposed to bound for all n's as well. So here we have this y, and then what we know is that y's in K, so y has to be an element of n sub delta of x sub I for some I equal 1 to up to p. Thus, the distance between y and x sub this x sub I is going to be less than our delta. So what we get is that the norm between f sub n of y minus f sub n of x sub I, that's going to be less than 1, or epsilon, and that's for all n. Okay, because the equine continuity. We're almost done with part A, and that's all we'll do today. Thus, we have the absolute value of the norms of f sub n of y minus f sub n of x sub I, like this, will be less than 1, and that's true for all n. Thus, we have minus 1 will be less than, this should have the norm of f sub n of y. Okay? That should all be. So here's the norm of f sub n of y, minus the norm of f sub n of x sub I, which is less than 1. And we'll add the norm of f sub n of x sub I to both sides. is going to be less than f sub n of y, which will be less than 1 plus this norm. Now, this was bounded, if you remember, by m for all n. So all this is true for all n's, for all n's. And so I can write down that f sub n of y is going to be less than 1 plus m, because this was bounded by m, and that's true for all n equal 1 forever, 1, 2, 3 forever. And so for all the y's, they're going to be bounded by this particular number. Okay? For all y, I had just a generic one. By this particular number doesn't depend on y. And this is true for all n. So that means that the sequence of f sub n's are uniformly bound. That's enough for this lecture. And we'll finish up the part B next time of this proof. Thank you very much.